Section 4.7 is on Newton's method. It is another application of the derivative. So Newton's method is a technique to approximate the solution to the equation f of x equals to 0. In other words, whenever you're solving f of x equal to 0, what we're doing is we're solving for the x-intercept of the graph, or you could think about it as the root of a function, or the 0 of a polynomial. So I may use these interchangeably throughout the lesson. If we look at this right here, the graph of some polynomial is given. It has 3 x-intercepts, roots, or zeros, and our goal is essentially to find this one. Again, there is some downside to this method. It would need to be used multiple times to find different ones, but it is ultimately going to find some 0. And again, we're approximating, so it may take several iterations to find the actual 0, or at least to go ahead and get it close enough to where the error is negligible. So here's how Newton's method works. You're going to first approximate, you're going to start by guessing a first approximation, which we will just denote with x sub 0 or x naught. So you approximate a solution to the equation f of x equal to 0. And it might be useful to have a graph here just to have a quick reference. So, for example, if this was like 1, and then this is 2, and then this is 3, and then this would be 4, it would be good to maybe make our first guess of 4, because it's pretty close. And we'll understand how this process will actually get us the value of the actual 0, or at least an estimate or approximation of it. So use the first approximation, x naught, which we stated above, to get a second approximation, x1, and the second to get a third, which we'll just note is x2, and so on. And the formula is going to essentially give us the next approximation. So if we want the nth plus 1th approximation, we'll get that by taking the previous approximation, and we're going to subtract the ratio f of x divided by, well, let me actually say f of x sub n. So again, we're going to take our first approximation, we're then going to plug it into the actual function, and then we're going to divide it by plugging that approximation into the derivative. So this formula feels a little arbitrary, but let's go ahead and see what it does and just have a brief conversation about where it comes from down here below. So if we look at this first graph over here on the left, let's read what the caption says. Newton's method starts with an initial guess x sub naught, or x naught, and under favorable circumstances, it improves the guess one step at a time. And we'll look at the unfavorable circumstances a little bit later. So you can see our first guess, and essentially what we're going to do is that formula is going to send us up and find the tangent line, and then we're going to look at the x-intercept from the tangent line, and that is going to give us our second approximation. So then we go up and find the tangent line at x sub 1, and then we go ahead and draw the tangent line, and then we see where the x-intercept is. So then we go back up, draw the tangent line at the point, consider the tangent line and its x-intercept, and if you continue this process, you can see we're basically getting closer and closer to this root right here that we're seeking. So where does this come from? Well, it really comes a little bit back from section 3.11, where you learn about linearization. So there's a lot going on right here. So let's just maybe kind of look at this one step at a time to see where this formula comes from. So the linearization, again, is just essentially if you zoom really close into the graph, you can tell that, or it's hard to tell the difference between the actual graph and the tangent line. So the linearization is just finding the tangent line at some given point. And remember what we said. We want the tangent line, its x-intercept. So in other words, what we're going to do is look at L of x equal to 0. L of x is referred to the linearization. A review of that, look back to section 3.11. Okay, so if L of x is equal to 0, aka we're looking to find the x-intercept of the tangent line, what we're going to go ahead and do is replace L of x with the actual linearization. So what would that be? You could actually see it right over here. Again, we'll just have to go ahead and solve this. If we go ahead and solve this for y, this is the linearization. So again, this is L of x. And what we get is the f of xn. And then when you add that to the other side, so that'll be added with f prime of xn times x minus xn, and that's still equal to 0. Okay, let's go ahead and solve this for x now. So to solve that for x, we're going to do a couple things. We're going to go ahead and subtract that over to the right-hand side, and then we'll go ahead and divide it this f prime. So what will that give us as x minus xn is equal to, let's see, we would have the minus f of xn in the numerator. Then we divide that f by f prime of xn. And then lastly, we add xn to both sides, and you get x is equal to xn, which is going to be minus f of xn divided by f prime of xn. So that right there, of course, is the x-intercept of the tangent line, which is the next approximation. So again, all of that is xn plus 1. Okay, so that's where it comes from. The rest of this lesson is just going to be getting the hang of using this formula and making sure we understand what we're doing at each step. So on the next page, we're looking at an actual estimation of irrational numbers. So we might find a decimal approximation of the square root of 2, which we're going to use this graph to do so by estimating the positive root of the equation f of x equal to x squared minus 2. And of course, if you were to solve this, what you would end up with is, more specifically, if you were to go ahead and set this equal to 0 and solve it, you would end with x equal to plus or minus 2, as square root of 2, excuse me. As mentioned earlier, the Newton's method will only find one of the roots, so we're looking for this one right over here. And the exact value, again, is irrational, so it goes on forever, so it's really hard to talk about the exact value. But the square root of 2 is approximately 1.41421, so on. So that's going to be our goal, is to get something right around there. So just to have it for reference, the formula is xn plus 1 is equal to xn minus f of xn divided by f prime of xn. So x1 is going to be equal to x sub 0 minus f of x sub 0 divided by f prime of x sub 0. So that, of course, is just applying the formula specifically to the zeroth, or the first approximation, and the second. So let's see, does it give us, yeah, it goes ahead and says start with x sub 0 equal to minus 1 for the left solution. Let's skip that right there. Our goal is just, again, to go ahead and find the positive root. So we're really just going to need to go ahead and do the second part. That is to say, we are going to take an approximation, or our initial guess, of x sub 0, and we're going to iterate a few times to find the actual, or find an approximation. So x sub 1 is going to be equal to x sub 0, so that's going to be 1, minus f of 1 divided by f prime of 1. Okay. Might be useful also to go ahead and just look at the derivative. So the derivative is 2x minus 0. Again, that's just the derivative of our given function. All right, so let's go ahead and simplify this. So this is going to be 1 minus the x squared, in this case 1 squared minus 2, divided by 2 times 1, which is going to be 1 minus a minus 2. Let's see, this will be 1 minus 2, or minus 1 over 2. So what we end up with here is going to be 3 halves, or 1.5. So you can see we're already actually closer to this 1.4. And just to make sure we understand what we're doing graphically, let me zoom over in over here. Our initial guess was x sub 0 equal to 1. So we go ahead and look at the tangent line there. So let me go ahead and draw that to the best of my ability. So let's go ahead and approximate. Actually, that was a little off, because again, we already saw that it should be at 1.5. So that's pretty good right there. So again, notice right here, this is 1.5. That is x sub 1. So just to maybe get some intuition on where we're going to go to next, let's change our color. We're going to go ahead and draw the tangent line to the graph. So if we draw the tangent line right here, it's going to be a little bit cluttered right here, but we could try to, can I zoom in any more? Yeah, a little bit better. You can see that this tangent line is getting really close to the actual value of that 1.4, 1, 4, 2, 1, so on. And again, we really, however, depending on how many iterations we want to do, is how accurate this will be. So let's do the next approximation. That is to say, x sub 2 is going to be x sub 1 minus f of x sub 1 divided by f of x, or f prime of x sub 1. All right, let's do this calculation. So this is going to be 1.5 minus 1.5 squared minus 2, plugging it into the original function, divided by 2 times 1.5. So this is going to be 1.5 minus, actually I did all of this computation a little bit ahead of time, so it's going to be approximately, just by the time you square all this and work it out, it's going to be 1.41667. So it's getting a little bit closer. And if you look at this, we have very little error at this point. We actually have the first 2 decimal places are correct. And something that's interesting to think about, if we just continued this process, if we just kept going and we found x3 and then we found x4, and supposedly if we just could go on to infinity and find basically the infinitieth, is that a word? Sure, infinitieth approximation, this would be exactly the square root of 2. Again, we don't ever really need that much accuracy, but it is kind of worthwhile to note what our goal, or what is going to happen if we continue this process. If we look down here, if we were to go, we have a table of essentially some of the accurate values. Well, we used to. Never mind, we don't anymore. I think if we were to actually do x sub 3, let me see. I computed that. That one is going to be 1.41422. So if you look at just even one more iteration, we even have two more accurate place values. So basically at x sub 3, the first 5 digits are accurate. At x sub 2, we had the first 3 digits are accurate. And again, like I said, if you went on to infinity with this process, you can get as much accuracy as you need. But that's Newton's method. Not too bad. The rest of this lesson just has some additional examples. So let's go maybe do one more together on the next page. use Newton's method to estimate the zeros of this function. Start with x sub 0 for the right solution and find x2, and we're not asking to do each case, but I graphed this one ahead of time. It has two solutions. Essentially, this graph maybe is just to have it in kind of our back of our mind is gonna be looking something like this. Again, this has two zeros right here and right here. Let's go ahead and find this one right here on the right. Find me. Okay. So, if you had the graph, you would see that this is approximately at 2. Actually, it wanted us to use 1 right there. So yeah, it's approximately at 2, but it wanted us to go ahead and use x sub 0 equal to 1. So that's like right here. So let's see what happens. So x sub 0 is equal to, x sub 1 is equal to x sub 0 minus f of x sub 0 divided by f prime of x sub 0. The derivative here, just for quick reference, let's put this in a different color. F prime of x is going to be 4x cubed minus 1. Again, just taking the derivative right there. So x sub 1 is going to be equal to 1, which they want us to use, minus f of 1 divided by f prime of 1, which is 1 minus, let's see, 1 to the 4th minus 1 minus 12 over 4 times 1 cubed minus 1, which is going to be 1 minus a minus 12 over 4 minus 1 is 3. So it's going to be 1 minus, or it'll end up being plus 4, and then it'll be 5. So what happened, it's a little bit hard to see right here, but we went down to the graph, drew a tangent line, and what we'll end up with is over here at x sub 1. So we're actually not, this is not a very good scale, but I guess maybe if something like that. So that right there is the 5. So what we would now do is we would go ahead and find tangent lines. So it'd be up here, we draw down, and it's going to be right around there. It just wanted x sub 2. So let's go ahead and find that. So x sub 2 would be 5 minus f of 5 divided by f prime of 5, which is 5 minus, let's see, 5 to the 4th minus 5 minus 12 divided by 4 times 5 to the 3rd minus 1, which is going to be, I did this calculation ahead of time, 5, this would be 625 minus 5 minus 12, and that is going to be 4 times 125 minus 1. So this is 5 minus 608 divided by 499, which is approximately 3.7816. And that right there to 4 decimal places is x sub 2. Couple other flavors to Newton's method besides finding the actual zeros, or estimating them at least, would be finding the intersection of functions. So you can see right here, if we kind of look at this, we're looking like the x value is, I don't know, maybe like 0.045. That's just a guess. So is x approximately equal to 0.045? So that would probably be a good candidate for your first estimation. But realize that whenever they intersect, that is the scenario where the two functions are equal. So that's what we have right here. And you can just basically say, okay, I need some sort of function. So just go ahead and set it equal to 0, and that will be the scenario that you will go ahead and apply Newton's method with. So if you set, so that would be cosine of x minus 2x, if we had set that equal to 0, or basically subtracted the 2x, and then you could use Newton's method from there. All right, on the next page, we have the graph of a very similar approach. You have two functions, this cubic function and this rational function. So in blue is the rational, and here's a cubic. Again, it's probably doing something like that over there on the left. It intersects right here. X equal to r as shown in the graph. Use Newton's method to again estimate r. So again, this r is maybe a little bit more than 0.8. So maybe you just basically say maybe x naught is equal to 1. Since that's pretty close there, start with a nice clean value. And then your function would just be the same principle. You'll just have the x squared times x plus 1, and you'll take away 1 over x after you had set them equal. And you could go ahead and distribute that x squared. And let's see, this it would make it a little bit easier instead of having to worry about the product rule. So that'd be x cubed plus x squared minus x to the minus 1. So that is then something that you can now use Newton's method to approximate the value of r. And again, however accurate would be you want, it depends on how many iterations you take. Okay, now the last two things to mention are those cases where it may not play out as nicely, where you might get stuck in a loop. So this is kind of alluding to in Calculus 2 an idea known as convergence. Intuitively, we try to answer the question of how many steps it takes to obtain an approximation of a desired accurateness. So here are a few facts about the convergence of Newton's method to keep in mind. So the first one is Newton's method does not always converge. So if you look at this scenario, you take initial guess, you find the tangent line, you go ahead and find the x-intercept of the tangent line right here, and then when you go ahead and do your next approximation, you'll notice that the tangent line, its x-intercept, sends you back to your first approximation. So we essentially have a looping that is going on here. If Newton's method does not or if it does converge, it converges to a root. And again, I mentioned this earlier, not all roots is going to converge to a root. And the tricky thing to realize is it's not always the closest one. That's what number 3 is saying. When Newton's method converges to a root, it may not be the expected root. So we have an example of this scenario taking place down here below. We're looking for this, actually this one over here on the left is the one we're searching. But you can see right here, we take an approximation that's fairly far away. So we hit the tangent line, or we draw the tangent line, look at its x-intercept to get our first approximation, draw another tangent line, look at the x-intercept, get our second approximation. You can see that we would converge to here. Basically, we're not going to get this one unless if we're like over here on this left part of the graph. And again, be careful. You're not always going to get the closest one. So you can see if you're looking here or looking for that root, you start right here in that same process, draw a tangent line like we do here, find its x-intercept to get our first approximation, and then repeat. You'll notice that this process actually gets us this root over here on the left. So it's a nice method to kind of introduce the idea of convergence and approximations, but it does have some downfalls. For example, you can only find one root, and you do have to make some sort of educated guess, and there might be the guess scenario that the guess actually never converges because you're kind of stuck in a loop. Anyway, that is Newton's method. I hope you enjoyed this lesson, as it is a very interesting application of the derivative.